Okey, Assalamualaikum, selamat pagi semua. Boleh dengar tak suara saya?
Salam doktor, dengar tak?
Boleh. Boleh doktor.
Okey, sekarang boleh dengar?
Dengar doktor.
Okey, skrin boleh nampak
Nampak?
Boleh sir.
Okey, nampak. Okey, selamat pagi. Assalamualaikum, selamat pagi semua.
Salam.
Okey, so saya dah upload planning materials. Okey. Learning materials from chapter 1. Okay, chapter 1 until chapter 7. Okay, chapter 1 until chapter 7, and also few example lah. Okay, few examples. Okay, I hope that all of you can look at it. Okay, this is a few example on chapter 1. And then I will upload more materials lah. Okay, so hopefully you can look at author. So our author will be official medium lah for our PNP. Okay, so far we have 45. Okay, 45 students for this section 3. Okay, today I will start on chapter 1. Chapter 1. So chapter 1, okay, what is chapter 1? So chapter 1 is an introduction to machinery principles. Okay, this slide has been prepared by Dr. Kok lah. Okay, Dr. Kok Buncin. Okay, so if any, kalau rasa tak dengar ke apa ke, just inform Okay, this is a basic lah. Okay, what is the outcome for this chapter? So at the end of this chapter, students should be able to point out the fundamental of electromagnetic in energy conversion. Number 2 is explain effectively the concept of rotational motion. And number 3, share the latest information of energy conversion devices. Okay, saya tak bawa digital pad pula hari ni. Okay. So for number 1, the fundamental. The fundamental is very important lah, how to understand the machinery principles. And then number 2 is regarding the concept of DC, the DC motor, DC machine, okay, and so on lah, DC, synchronous motor, and so on. And number 3, they share the latest information, okay, of energy conversion devices. Okay, this is the outline lah. So the outline, we have a few outline. Okay, rotational motion, Newton law, power relationship, okay, the magnetic field, magnetic circuit, okay, what is the Faraday law, induced voltage from magnetic field, induced force on the wire, and induced voltage on a conductor moving in magnetic field. Okay, so as we know that our Earth have a magnetic field, so this is the view lah, okay, the view of our Earth's magnetic field. So we have a geographical south pole, and then we have a not magnetic pole here, and then also geographic north pole. Okay. Okay, so benda ni ialah fundamental I think you have learned it in primary and secondary school lah. Okay. Now in degree we need to apply. Okay, we need to apply. Okay, like pole repels, unlike pole will be attract. This is the concept lah. Okay, and then also we have a right hand grip rule. So if we grip our right hand, so the thumb will point to the current flow. Okay, current flow B, and then okay, this is B. Okay, okay, if current, okay, so for this concept, if we put in electric fundamental, so if we put a connection between a battery from positive to negative, okay, the current will flow from positive to negative. And then if we apply our right hand rule here, so we can know the B. Okay, B. And then also this is an example lah. Okay, example. Okay, this is the current flow direction, and then the magnetic field direction. Okay. Okay, so this is the battery lah. Okay, positive terminal and negative terminal, and then the current will flow from positive to negative. Okay, and then here we have a solenoid. Okay, this is the current flow. This is flow in, Kx, and this is the current out. Okay, ini keratan rentas lah. Okay, keratan rentas solenoid ni. Okay, and then also the Fleming right hand rule. We have a left hand rule. So this is the direction of force, and then we have a magnet here, north pole, and then this is the south pole, and then this is the cable lah. Okay, if we put the cable here, so there will be magnetic field pass through this point, and this is the direction of current. Okay, and then also this is the magnetic field. Okay, the magnetic field. Ini konsep motor. Kita ada north pole, south pole. You boleh tengok kalau macam apa, DC motor yang kecil-kecil tu. If we apply a positive and negative, the current will flow, and then there is a coil inside the. So this is the carbon brush lah. Okay, carbon brush. So the current will flow from positive to negative. Okay, this is the current going, force will be going down, and then this is the magnetic field. So what is the effect of current through the magnetic field? Okay, this is an example. Okay, example B in, and then the current akan macam ni lah. Okay, so and then after that current akan macam ni. Okay. Okay, this is the application lah, the application of a right hand rule. Chapter ni banyak teori Okay, this is a battery, and then we have a north pole, and then we have a south pole, and then the current pass through in between north and south pole. So the force will be going up, and then if we change the terminal, okay, if we change the terminal from negative to positive, the force will be going up. For this case, the force will be going down. This concept has been applied in DC motor. Okay, if we want to change the direction of the motor, so we need to reverse the polarity. Okay, we need to reverse the polarity. Also, we can apply the in converter lah. So kita boleh gunakan converter such as H-bridge converter. Pernah dengar tak H-bridge converter? So we have a four switch, so we can reverse the terminal. Okay, H bridge converter. Okay, H bridge converter, we have four switch. Okay, this is your motor. Okay, and then we have a okay, so we have a four switch. Usually we are using MOSFET or IGBT lah. MOSFET and IGBT. So to make sure that the motor rotate in clockwise, so we need to turn on this switch and this switch. So the current will flow from positive to negative. Okay. If we want to operate the motor in counterclockwise, so we need to turn on switch, this one. Okay, the current will flow from positive to negative, but in reverse direction, from here to here. Okay, so this is the concept now, how to rotate the motor in clockwise and counterclockwise. Okay, so this is an electric machine, consists of rotor. What is a rotor? Rotor is a rotating part, and then the stator. What is stator? The stator is a static. Okay, and then also we have a shaft. Okay, this is the shaft. This is the stator, and we have a rotor inside. So, and then we have a direction of rotation, counterclockwise, positive, and clockwise will be negative. So for this case, we have three. Okay, we have three. A bar, okay, A dash lah. A, and then we have C bar, C, and then B bar. Okay, so to make it moving, they rotate, to make the motor rotate, so we need to apply lah. For this case, we have three terminal. That's why we have red, yellow, and blue lah. Okay, red, yellow, and blue. Okay, sine wave. Okay, so red, yellow, and blue, the displacement between red, yellow, and blue is 120 degrees. Okay, maksudnya beza antara waveform ni ialah 120 darjah. So we have, if we have a three terminal, okay, if we have a terminal and then we apply with red, yellow, and blue incoming supply, so dia akan menolak lah antara satu sama lain disebabkan oleh beza fasa 120 darjah. Okay. So how to make it rotate clockwise and counterclockwise? So we need to reverse one two terminal, any terminal, either red, yellow or yellow, blue. So dia akan reverse. Okay, that's why we have apa tu kita panggil dia reverse starting motor. Kita ada motor, reverse motor, kita boleh reverse dan sebenarnya kita change the phase, two phase. Okay, what is the difference between rotational motion and linear motion? So we have angular position for rotational motion in a radian or degree. In linear motion, we have a linear distance r, okay, in meter. And also we have angular velocity omega. The unit is in radian per second. And also we have linear velocity v in linear motion meter per second. Okay, in rotational motion we have angular acceleration, okay, equal to d omega over dt. In linear motion we have a linear acceleration. The unit will be meter per second squared lah. Okay, a dv over dt. So dv is a velocity. And also we have a rotational motion torque. The unit in Newton meter. And in linear motion we have a force. The unit is a Newton. The formula is F equal to ma. Okay, this is the related formula for this chapter. We have Newton law of rotational. Okay, torque equal to the net applied torque in Newton meter or LB FT, and J is the moment of inertia in kilometer squared. Okay, or you can use this. Normally we are using this unit. Okay, and then also we have a work W, integrate from tau d theta. So if a constant, so we can use this formula. And also we have a power P. Okay, the unit in watt. And also normally we are using horsepower lah for motor. Now we are using horsepower. Okay, this is some example with a solution. So how to calculate the speed, okay, in radian and revolution per minute, RPM. Okay, a flywheel with a moment of inertia of 2 kg per meter squared is initially at rest if a torque of 5 Newton meter. The direction is in counterclockwise is suddenly applied to the flywheel. What will be the speed of the flywheel after 5 seconds? So we can you need to express this that speed in both direction, both radian per second and revolution per minute. So from here we can calculate the speed in radian per second and in revolution per minute. Make sure that you're familiar how to convert the radian and revolution per minute. Okay, I'm not going to go to the example. Okay, so the operation of electrical machine can be explained in four general principles. So we have first electromagnetic action, second one is a transformer action, third is a motor action, and number four is a generator action. So what is a electromagnetic action? So an electrical current causes a magnetic field which surrounds it. Okay, when the current reverses in direction, so does the magnetic field also reverse. The magnetic field is a condition resulting from the electrical charge in motion. Okay, this is a simple electromagnetic. So we have a wire connecting to nails, and then we connect to positive and negative. Okay, so this is the magnetic field, and this is the induced current in a piece and the current in a coil. Kamu boleh tengok eksperimen dekat YouTube lah, dia buat macam mana untuk yang simple number one ni. Okay, so this is the production of magnetic field. Okay, terms ni you need to remember lah. What is H? What is B? Okay, H is a magnetic field intensity, ampere turns per meter. And then we have I net is a current, and dl is differential element of mean path length. Okay, this is the A. And then this is the length, this is the flux flow, and this is the current. This is the number of turns. Okay, what is H? Okay, H is a magnetic field intensity vector. The formula is H equal to magnetomotive force divided by mean path length equal to Ni. N is number of turns, I is the current flow, L is the length. So the strength of the magnetic field flux produced in the core depends on the material. So usually we are using ferromagnetic material of the core, and then also we have a magnetic flux density B. The unit will be Weber per meter squared or Tesla. Okay, B equal to UH. Nu H. Nu, what is nu? Nu is magnetic permeability of the material. The unit will be Henry per meter. For free space permeability, mu naught given by mu naught equal to 4 pi times 10 power of negative 7 Henry per meter squared. How to calculate the relative permeability? Mu R. Mu R is equal to nu divided by mu naught. Okay, and the magnetic flux density can be written by B equal to nu H equal to nu Ni H equal to Ni divided by L. Number of turn, the current flow, and the length. Okay, so next will be the total flux is given in a given area. Flux will be equal to integration B dot dA lah. Okay, if the flux density is a constant, flux equal to B times A. Okay, and also the total flux in the core is given by this equation, flux equal to BA. So, which is nu and I divided by L times A. Okay, A is the area, the surface area. Okay, losses in electromagnetic core. Okay, we have a losses in electromagnetic core. Core loss is extremely important in practice since it's really impacted by the operating temperature, the efficiency, and the rating of the magnetic devices. There is two main energy losses, which is we call it as a hysteresis loss and eddy current loss. Okay, this is the hysteresis loss, BH curve. Okay, this is we call it as a BH curve. Okay, if we apply a AC current, assume flux in the core is initially 0. As current increase, the flux trace the path from A to B, which is the saturation curve. When the current decrease, the flux trace out a different path from the one when the current is increased. When the current decrease, the flux trace out from part B, C, and DE. Okay, so will be going up, and this is the saturation. Okay, will be going down from B, C, D, and E. And then when the current is increased, it traces out part from E, F, G, and B. Okay, the amount of flux present in the core depends not only the amount of current applied to the winding of the core, but also the previous history of the flux in the core. Hysteresis depends on the preceding flux history and the resulting failure to trace the flux path. Okay, this is the explanation for the BH curve. Okay, when a large MMF is applied to the core and then removed, the flux path in the core will be A, B to C. And then when the MMF is removed, the flux does not go to 0. Okay, this is how the permanent magnet are produced. To force the flux to 0, the amount of MMF known as a forcive MMF must be applied in the opposite direction. Okay. Okay, this is the part of AD current perpendicular to the flux. This is the solid core, laminated core. Okay, ni baca je lah. The time charging flux induce voltage within the ferromagnetic core. This voltage cause of swirl of current to flow within the core, which is AD current. Energy is dissipated in the form of heat because this eddy current are flowing in the resistive material. And the amount of energy lost to eddy current is proportional to the size of the path they follow within the core. And then in order to reduce the energy loss, the ferromagnetic core should be broken up into a small clip or lamination. Okay, this usually applied to our motor. So we need to slice lah, kita slice or laminate and build the core up to the strip. Okay, and an insulating oxide or resin is used between the strip so that the current path for eddy current are limited to small area. So kalau kita nampak kita buat tu, kita lapik-lapik dengan lapisan yang nipis, and then in between the strip tu kita letak resin, okay, to reduce the eddy current lah. Okay, this is the analogy between electric and magnetic field. So we learn electric circuit kan. Okay, what is our electric circuit? So we have a V, positive and negative, and we have a resistance. Okay, kita ambil battery and then wire and connect to resistance or bulb lah, okay, lampu ke apa kan, as a load, and the current will flow from positive to negative. So we can calculate the current, voltage of the resistance. So I equal to V over R. In magnetic field, okay, magnetic circuit, so we have also the supply. Okay, we use F lah. F equal to Ni. What is N? N is number of turns and I is a current. Okay, and then flux will flow from positive to negative, and also we have a reluctance. So this is the formula. Flux equal to F. F is a magnetic force divided by reluctance. Okay, this is an example. So we have E, positive and negative. So this is the flux, and this is number of turns. Okay, MMF is F equal to flux times R. Okay, flux equal to BA, or we can calculate using this formula, nu ni divided by the length times the area, or number of turns the current, nu the area divided by the length is equal to F equal to nu A divided by the length. Okay, R, the reluctance, equal to the length divided by nu A. What is nu? Nu is equal to nu is equal to nu R nu no. So if the reluctance in series, the R equivalent will be equal to R1, saya panggil dia R je lah Okay, R1 plus R2 plus R3. So if the reluctance in parallel, 1 over R equivalent is equal to 1 over R1, 1 over R2 plus 1 over R3 and so on. Okay, ini mana yang rasanya ex diploma, poli or UTSM, saya rasa you dah belajar benda ni. Just review balik lah. Okay, this example Okay, this is example. The ferromagnetic core is shown in the figure. The three sides of core are of uniform width. Maksudnya dia beza beza dari segi width dia lah. While the fourth side is somewhat thinner. Okay, ini 15, ini 15, ini 10. Okay. Okay, the depth of the core is 10 cm and others dimension are shown in the figure. Okay, there is a 200 turns coil wrapped around the left side of the core, assuming relative permeability is given by nu R is equal to 2500. How much flux will be produced by 1 ampere input current? Okay, so dia nak cari nilai flux. Flux macam mana simbol dia? Okay, flux ni. Okay, so from here we can look at this dimension. Dimension. Okay, so macam mana kita nak divide? So we need to divide by 2 lah. Okay, divide by 2. So kita kena tengok dia punya lebar. Okay, so you boleh ambil daripada sini. Okay, ini 1 dan 2. Okay, 1 dan 2. So kalau you ambil macam ni, you kena ambil sini dimension, dia punya length dia sini. Sini. Kita katakan ini A. Sorry saya tak bawa digital pad, so tulisan ni sikit pakai mouse je. Okay, so from for A, the length will be, kalau you ambil macam ni lah. Okay, the length will be from this one, let's say A to B, this is B, C, and sorry, sini. Okay, A, B, C, and D. And for B, from A to D, kat sini. So, okay, the core can be divided into two regions. Okay, first the single thinner side, and number two, the second one is the other three sides taken together. The magnetic circuit corresponding to the core is shown in the figure. So this is the magnetic circuit. The mean path length of region 1 is 45. Okay, 45, 30 plus 7.5 plus 7.5. Okay, 45. Okay, faham And the cross-sectional area is 10 times 10 cm, which is 100 cm squared. Okay, the depth of the core into the page is 10. Maksudnya dia macam ni lah. Okay, dia punya depth dia 10 cm. Okay, therefore the reluctance in the first region can be calculated by using this equation. Okay, all the unit you need to convert from cm to meter. Okay, sebelum ni kita dapat 45 cm kan, so you need to convert to meter. 0.45 is the length yang ni lah, yang ni. Okay, and then divide by new times A1. So dinamakan dia sebagai A1 lah. Okay, what is new? New is new R, relative permeability, and new naught. New naught is a constant. So ni kalau you tengok dekat calculator kita, kalau dulu lah calculator saya kat dulu tu, dekat belakang dia punya cap tu ada, cover tu ada tulis. Okay, new naught is a constant value. 4 pi times 10 power of negative 7. Okay, sometimes for new R is depend on the material. Okay, in some case they given you the table, so you need to read lah. You need to calculate the new R. In some question, they are given, so you need to use lah. So this is 2,2500 times new naught times the area, the surface area. Okay, the surface area is 0.01. Okay, this is 10 cm times the depth is 10. Need to convert. Okay, so the reluctance for R1 will be 14300 ampere turns per Weber. Okay, faham So dekat sini yang biasa
Sir.
Kelas, ya.
4 pi darab 10 negatif 7 tu dapat kat mana?
Ini memang given.
Kau memang given. Okay,
Ha,
terima kasih
ini
sir.
memang new note tu memang tetap. Okay, nilai yang tetap. Tu saya kata kalau you tengok dekat calculator tu, biasanya dekat cover tu belakang tu ada tuliskan formula H. Biasa ada lah benda tu. You just call back. Ataupun kalau you boleh ingat,
Kena
file,
ingat ke sir?
ini biasa memang nilai yang tetap lah. So you just akan datang mesti you ingat dengan benda ni.
Okay, terima kasih sir.
Okay, so darabkan ni and then kita dapat ni lah 14300. Okay, and then the mean file for length of region 2. Okay, region 2, what is your region 2? Region 2 ni lah. Okay, this is your region 2. The length ni kena ambil from center You must measure from center. Okay, this one. Jadi kita dah ambil sini. So ini kita ambil sini lah. Okay, 30 plus 7.5 plus 7.5 plus 30 plus 7.5 plus 7.5 plus 30 plus 7 sampai sini lah, plus 30. So the total length L2 will be 130 and the cross-sectional area is 15 times 10. Okay, panjang darab lebar. So the 15, okay, this is 15. So this is 10. Meaning that the surface area. Surface area ni lah. Kalau kita potong ni. Ni. Surface area dia. In case the size, okay, the size of ferromagnetic core is different, so kamu tak boleh, kalau size tiba-tiba dekat sini size dia 5, kamu tak boleh campurkan semua sebab dia dah lain. Kena ada 3 reluctance lah, 3 R. For this case we only have one types and the dimension is different. Okay, so here 150 cm squared. So you need to convert to meter. Okay. So saya ingatkan sekali lagi, Kelas biasanya student Kelas from lupa lah Kelas mistake. You need to change from cm to meter. Okay, therefore the reluctance in the second region is R2 divided by length 2 divided by nu times the area 2. Okay, 1.3 meter divided by 2500 times the nu naught times the area. Okay, 27600 ampere turns per meter. So and then from previous formula, dia sama macam resistance lah. So we can if in series, macam ni case ni, for this case in series, so you just plus lah R1 plus R2, then you can get the R total reluctance. So the total reluctance R equivalent is equal to R1 plus R2. Okay, just add R1 and R2. And the R equivalent will be 41900. Okay. Okay, so ini F equal to Ni, given that the number of turns is 200 turns and the current flow is 1 amp, so the F will be 200 ampere per turns. Kena ingat lah, F equal to Ni, flux equal to B times A, R equal to length divided by mu times A. Okay, mu is equal to mu naught mu R. Macam tu lah, kita kena ingat benda ni. And then try to, if you get this question, you need to convert lah macam ni kan. Okay, you need to convert to magnetic field macam ni. Okay. The total flux in the core is given by flux equal to F divided by R. Flux ni macam tadi lah. Flux is I. Kalau elektrik sikit I equal to V over R. Kalau dekat magnetic circuit is flux equal to F divided by R. Okay. This is your F. This is your flux. And then this is your reluctance. F equal to F, this is reluctance. F equal to N number of turns times the current. Okay, so for this case we have 200 ampere per turns divided by the total reluctance. So the flux will be 0.0048 WB Weber. Okay, faham eh? Okay, this is an example. Okay. Okay. Figure shows a ferromagnetic core whose mean path length is 40 cm. There is a small gap of 0.05 in the structure of the otherwise whole core. So dia ada A gap kat sini. Okay. Dia punya dimension ialah 0.05 cm. The cross-sectional area of the core is 12 cm squared. Okay, cross-sectional ni lah. Okay, this is A. This is length L. The relative permeability of the core. What is relative permeability is mu R is 4000 and the core wire of the core has 400 turns. This is N. Assume that bringing in the air gap increase the effective cross-sectional area of the air gap by 5%. Okay, assume that bringing in the air gap increase effective cross-sectional Maksudnya dekat sini flinging ni dia akan menyebabkan you punya cross sectional tu increase by 5%. So given this information, A, find the total reluctance of the plug path ion plus A gap and the current required to produce a plug density of 0.5 Tesla in the A gap. Okay, so first what you need to do is to convert this ferromagnetic core to equivalent magnetic field. Sorry, equivalent magnetic circuit. Okay, dia akan jadi macam ni. Dia akan jadi macam ni. So the first one is the reluctance for this one, and the second one for the A gap. R1, R2. Okay, reluctance for this and reluctance for the A gap. And then this one F equal to Ni, and the flux flow from positive to negative. RC is the reluctance of core, reluctance of A gap. Okay, ni tak kisahlah you nak pakai apa. You nak pakai RC ke, RA ke, R1 ke, R2 ke. Okay, this is the A gap, RAG ke, okay. Kalau salah dekat sini, salahlah kamu punya jawapan. Okay, first you need to calculate the reluctance for R core, RC, R core. Okay, LC is 45, LC 40 Okay, 40, 0 tukar convert to from cm to mm. And then the new R is given by 4000, new naught is 4 pi times 10 power of negative 7, and the cross-sectional area is 0.0012 meter squared. And then this is the answer, 66300 ampere turns per Weber. Okay, so here the effective area of the A gap is 1.05 times plus cm squared is equal to 12.6 cm squared. So the reluctance of the A gap is, ini yang ni soalan ni nampak. Assume that the flinging in the A gap increase the effective cross sectional area of the A gap by 5%. Okay, 5%. Maksudnya existingly the A gap is 100% and increased by 5%. So you need to times 1.05 lah times 12. 5.6 cm squared. Okay, untuk A gap, RAG apa ke? Okay, RA equal to LA. LA is 0.05 in cm, so you need to convert to meter and divide by mu naught. Okay, because the A gap is only formed by air. There is no ferromagnetic core, so you need only 2 times the mu naught. What is mu naught? Mu naught is 4 pi times 10 power of negative 7 times the cross-sectional area increased by 5%, 0.00126 meter squared. So this is the answer. 316000 ampere turns per Weber. Okay, ada nak tanya kat sini? Any question? Okay, so
Boleh saya
Ha,
boleh saya ulang yang untuk yang penambahan 5% tu. Dia
okay.
kira kat mana?
Oh, ni lah. So the 5% this one is relate to this statement. Okay, assume that the fringing is in the A gap, increase the effective cross-sectional area of the A gap by 5%. Okay, kalau saya kata, okay, duit kamu disebabkan apa, ekonomi yang baik, duit kamu naik 5%. Jadi kalau kamu ada RM10, duit kamu akan dapat RM10.50. Betul? Okay, macam mana nak dapat RM10.50? Darablah dengan 1.05. Okay. Kalau saya kata, kalau this question, okay, assume that the fringing decrease the effective cross-sectional area in the A gap by 5%. Maksudnya apa? Maksudnya you kena darab dengan 0.95. Faham tak?
Faham saya.
Okay. Okay, so due to the fringing effect, for this case, the cross-sectional increase 5%. Okay, so this is the new area due to the fringing effect. Okay. And then we can calculate the total reluctance. For this case, you just add lah, because the reluctance are in series. Okay, based on this magnetic equivalent circuit, so the reluctance are in series. You can add RC and RA. Okay, so the RC, R equivalent will be RC plus RA. So the total reluctance will be 382,300 ampere turns per Weber. Okay, note that the A gap contribute most of reluctance, even though it is 800 times shorter than the core. Okay, so kalau kita tengok kat sini, 6 kali 6, 36. Okay, lebih kurang So kalau kita tengok kat sini, dekat sini kalau core tu ada, kalau kita punya construction of ferromagnetic core, so we give a gap. Okay, we give a gap. The reluctance will be greater lah. Okay, ni A gap. Nampak? Compare to the core. Tapi length dia, ni length dia kecil je. 0.05 cm je. Okay. Tapi dia contribute to more reluctance in your magnetic circuit. Okay, and then B, the equation F equal to flux times reluctance, since the flux equal to BA, so you need to remember lah this one. And F equal to NI, this equation becomes NI equal to BAI. So we can calculate I equal to BA times reluctance divided by number of turns. B is 0.5. The dimension is, ini dekat A gap kalau kita tengok soalan tadi. You look at the question B. What is your question B? The current required to produce a flux density 0.5 Tesla in the A gap. Okay, in the A gap. Okay, so 0.5. So the area is 0.0126 meter squared, and the reluctance is 300 divided by N. Okay. So the current will be 0.602 N. Okay, notice that since the air gap flux was required, the effective air gap area was used in the above equation. So I hope that you can understand this simple question. Right? Simple question. First, you need to convert to magnetic circuit. Even though the question do not ask you to draw this magnetic circuit, so for your further understanding, so you need to come up with this one. Easy to understand. Okay, this one is a gap. Okay, let's say this one. Okay, ini katakanlah ini. This side is different material. Okay, this side onward from here to here. Okay, ini material lain. Ini material A. Ini material B. And then also A gap. So the magnetic circuit will be, there is three reluctance. Okay. Satu, this RA, RB, and RC. So the dimension from here to here, and from here to here. Right. So for this case, we only the ferromagnetic only formed by single apa tu, ferromagnetic core lah. Kalau dia ada banyak, you kena buat part by part. Okay, so we go to next principle 2, transformation. Okay, ni eksperimen lah. Biasa SPM you dah buat kan. Okay. The changing magnetic field cause a voltage in a circuit through which is pass. So kalau kita test and then kita sambung pada voltmeter or ammeter, if we put a magnet pass through the solenoid, and then we can look at the meter lah. So the meter can be moved in and out. The change can cause by the changing of current producing the magnetic field, or by moving the source of the magnetic field. Okay, this is a transformation. So the transformation, this is the primary, and then this is the secondary. Don't care about the step up or step down. The incoming will be the primary. In some case, the primary will be less than the secondary. Okay, kadang-kadang dia step up, dan kadang-kadang kita step down. Okay. So this is the primary, and then if we apply with sine waveform, maksudnya supply lah. We work supply with the supply, and then this is the number of turns lah. number of turns will be contribute the output in either step up or step down. Okay, number of turns in primary, number of turns in secondary. And then this is the laminated core. Laminated core maksudnya dia berlapik-lapik to reduce the eddy current losses. Okay, this is the flux, and then this is the output. The output. Okay, actually there is no connection between primary and secondary. Only the mutual connection untuk transformer. Untuk transformer ni, dia tak ada sambungan antara primary dan secondary. Dia lebih kepada magnetic circuit. Okay. Sebab tu kita gunakan transformer ni dekat mana? Dekat transmission line, dekat transmission line macam. And then simbol transformer macam mana? Biasa macam ni kan transformer. And then kita ada ni. And then kita ada. This is the transformer symbol. Okay. There is no connection between primary and secondary. Only the mutual connection. That's why if there is something happen, short circuit or any failure, fault or other effect happen in the secondary, it would not affect your primary side. Dia takkan effect pada kalau berlakunya short circuit ke apa ke, dia takkan effect pada you punya primary side. Dia akan berlaku pada sini je lah, secondary je lah. Ataupun kalau berlaku short circuit ke apa ke dekat you punya circuit, dia takkan effect you punya secondary. Okay, contoh macam rumah kamu ada short circuit, dia takkan pergi rosakkan transmission line punya distribution kat sini. Dia akan berlaku kat sini je, because there is no connection between primary and secondary, only mutual connection. Itu konsep transformer. That's why we learn transformer and also we learn the electric machine. Okay, if this is a Faraday law. If a plug pass through a turns of a coil of wire, a voltage will be induced in the turns of wire that is directly proportional to the rate of change in the flux in respect of time. So in a mathematical form, E induced equal to negative N divided by d flux over dt, which is E induced is a voltage induced in the N turns of coil. Okay. Okay, and then this is a Lenz's law. Lenz's law. What is the definition of Lenz's law? The direction of the voltage built up in the coil is such that if the coil N were short circuit, it will produce a current that would cause a flux opposing the original flux change. Okay, this is the definition of Lenz's law. Ini formula lah. Okay, this is a motor action, principle 3. An electrical current in magnetic field experience a magnetic force perpendicular to both direction of the current and the direction of the magnetic field. The force is proportional to the current and to the strength of the magnetic field. Okay. Okay, this is a right hand rule. And then this is a generator action. The motor action and the generator action actually is the motor itself. Motor tu sebenarnya kita boleh mesin lah. In general, we call it as a machine. Dia boleh berfungsi sebagai motor dan boleh berfungsi sebagai generator. Kalau you supply voltage, dia akan bergerak sebagai motor. Kalau you rotatekan dia punya shaft tu, dia boleh generate electricity. Okay, this is an example of a generator action. Habislah chapter 1. Okay, ada soalan? Any question?
Tak ada Ustaz. Okay, so we look at a few example. Okay, saya dah upload dekat water, so just review lah. Okay, review on the question. Okay, example 1. Example 1. Okay, ini saya pick up from some book lah. I'm not sure, PC Sen book. Okay. Okay, in the magnetic circuit of figure 1A, the relative permeability of the ferromagnetic material is 1200. Okay. Neglect the magnetic leakage and fringing effect. All the dimensions are in centimeters, and the magnetic material has a square cross-sectional area. Determine the A gap flux, the A gap flux density, and the magnetic field intensity and the A gap. Okay, so this is the given figure. Okay, if you look at here, there is two pipe. Okay. Okay, number one is
Okay, so dia hanya satu material kat sini. Okay, satu material. And from here you need to come up with magnetic circuit. Okay, this is the magnetic circuit. F1, F1, F2, and then this is the reluctance measured from B, A, F, E. Okay, B, A, F, E. Jangan ambil sampai ujung from the center. B, A, F, E, 1 plus 50 plus 1. Okay, plus 1 plus 1 plus 50 plus 1 plus 50 plus 1. So this is the length. Okay, kat sini. And then dekat tengah-tengah ni ada berapa reluctance? Ada 2. Okay, ada 2 from B to E tapi minus dengan 0.5. Maksudnya dekat sini ialah 50. Okay, 50 plus 1 plus 1 minus 0.5. Okay, so this is the reluctance, the length for reluctance RBE. And then also we have a A gap. A gap RG. What is the length? The length is 0.5 cm. And we have the fourth one is from B, C, D, E. Okay, the length. Jangan salah ambil. Salah ambil habis lah. This is the N2. F equal to Ni. Okay, this is the magnetic circuit. Okay, F1 if F equal to Ni equal to 500 times 10 ampere. Okay, same for F2, 500 times 10. Nu is 1200 times nu naught. Okay, so inilah yang penting ni, you kena come up with this length. Kalau macam kat tengah ni, you nak buat 2 pun boleh. You can calculate reluctance. Okay, RB katakan sini Z. From B to Z. Okay, 25 minus 0.5 plus 1. Okay, boleh lah. Tapi banyaklah calculationnya. Okay, ini dia punya tu. R reluctance for RA. Okay, reluctance for R B from B, A, F, E. And reluctance for B, C, D, E equal to, okay, kalau dimensionnya sama, materialnya sama, so jawapannya akan sama. Okay, and then the A gap. A gap and then the center, reluctance in the center. Tengah-tengah ni. From B to E. Okay, from figure 1, the loop equation. Okay, the loop equation, ini kita gunakan sama. Dia macam circuit analysis. Circuit analysis, kita boleh apply. Sebab dia magnetic circuit, jadi kita boleh apply lah. You nak apply Thevenin ke, Norton ke. Okay, as long as konsep tu betul lah. The loop equation. The loop equation maksudnya dia buat loops equation. Okay, macam ni. And then F tambah-tambah dapat equation ni. Okay, this is first equation, second equation. And then substitute equation 1 into equation 2. And then we get the flux. And then the A gap flux, we can calculate the A gap flux. After that, we can calculate the A gap flux density. And the last one will be the magnetic field intensity in the A gap. So I hope that you can go through this example. Okay, ada nak tanya?
Tak ada je.
Ada sir.
Okay, so example 2. Example 2 this given by this figure. Okay, the magnetic field of the figure has a core relative permeability of mu r is 2000. The depth of the core is 5 cm. Okay, the core has 400 turns and carries current of 1.5 ampere. So next you need to come up with the magnetic equivalent circuit. F equal to Ni. This is N, this is I. This is the reluctance. Kita ada A gap, so just satu je lah. Kecuali kalau dia ada dua material kat sini. Dua material yang berbeza. So you need to come up with two reluctance. Kalau ada tiga material yang berbeza, combine in one core, so you can ada tiga reluctance. So faham Sebab nilai mu tu akan berbeza. Okay, if there is a three different material in the magnetic circuit, it will cause different relative permeability sebab material tu berlainan. So you kena buat satu. For this case, only one types of material, which is 2000 mu r dia. So kena satu je lah. Okay, so this is very direct question. Find the flux and flux density in the core. So you need to calculate lah. Okay, to calculate R1 equal to length divided by nu times cross sectional area. L1 divided by nu naught times the area. Okay, sekali lagi saya ingatkan jangan lupa convert from cm to mm. Sorry, meter. And so just substitute. Okay, the length. And we get the reluctance for R1. Okay, what is F? F equal to Ni 400 times 1.5 ampere. 600. And the flux one, flux ni macam current lah flux equal to F divided by R. So F is 600 divided by the reluctance, 6.283 milli. Good. And we can also calculate the flux density. Oh, C2 dengan C ni sama. Okay, ada soalan? Faham senang kan?
Boleh lah sir. InsyaAllah. Tak ada soalan.
Okay, next week I will upload a few example for your reference lah. Okay. Okay, so we have complete our chapter 1. Okay, chapter 1. Sebenarnya saya bukan expert dalam mesin lah. Mesin ni siapa Dr. Ewan, okay, Prof. Ewan, Dr. Zarafi, Dr. Marizi, Dr. Rozia. Okay, itu dia ada satu tim lah, focus group mesin. Saya bidang power E lah, okay, power electronic. Saya Dr. Usman Rashid, dekan kita, Dr. Samsul Aizam, Dr. Wahyu, Dr. Jabbar, okay, itu power electronic. Jadi benda-benda ni semua basic lah, basic. So ada soalan? Tak ada soalan, so hopefully you can understand lah chapter 1 ni. Very basic introduction to machinery principles. So mana yang dah belajar masa diploma dulu, saya rasa benda ni just refresh balik lah, refresh balik. Untuk machine ni, please go through a lot of example, example. Sebab kita banyak formula dekat machine ni. Okay, so kalau tak ada soalan, kita jumpa minggu depan. Any update material ke, saya akan upload dekat author lah.
Baik sir.
Okay, so terima kasih semua. Assalamualaikum. Salam sejahtera.
Terima kasih, sir.
Okay, thank you.
Terima
Thank
kasih,
you
sir.
sir.
Thank you, sir.
Salam, terima kasih,
Thank you,
sir.
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 Thank you,
Thank you,
sir.
sir. Thank you, sir.
Thank you, sir.